Question B1. In the photoelectric effect, electrons are emitted from a metallic surface only if the wavelength of light incident on the surface is below a certain value called the threshold wavelength. Explain this observation. So, according to the photoelectric effect, energy comes in light in packets of energy, and we call those photons. So, photons, and they have energy equal to hf, or if we use our formula that C is equal to frequency times wavelength, we would have frequency is equal to speed divided by wavelength, so we can change this formula to that. So if this photon has got the required energy, we call that the work function. If it has a work function, this is the minimum amount of energy that is required to remove an electron from a metal. If it's got that amount of energy, that photon, then it will be ejected from the surface. Now, the wavelength obviously here, because we've got an inverse relationship, the wavelength needs to be a minimum value. You see where it says over here is below a certain value. So if this gets too big, then the energy gets too small, and therefore it won't have the required energy. So it needs to be below a certain value. Question B. We have a monochromatic source of power, 3 watts, emits light of a wavelength of 4.6 times 10 to the negative 7 meters. All the light is incident on a metal surface and causes electrons to be emitted at a rate of 4 times 10 to the 10 per second. So this is per second. The threshold wavelength of the metal is 5.5 times 10 to the negative 7. So that's the maximum wavelength where you will get electrons emitted. If it is longer than that, if the wavelength is bigger than that, the energy will be too low and no electrons will be emitted. So calculate the photoelectric current. So we see here in looking at this, let me just erase that. We see that we've got 4 times 10 to the 10 electrons per second, and each electron has a charge of 1.6 times 10 to the negative 19 coulombs. So when we multiply that out, we would get 6.4 times 10 to the negative 9. And because this is a coulomb per second, this is a per second value, and this is a coulomb. A coulomb per second is an amp, which is a current. The work function of the metal. Now we know that E is equal to HF, as we've discussed before over here, and then we are given here that you've got the threshold wavelength as this. So I'm going to put this formula in terms of wavelength, HF over C, sorry, HC over lambda, let's take it out, HC over lambda, and if I put that all in, now remember your H is Planck's constant, which is 6.63 times 10 to the negative 34 that you'll find in your data booklet, and you have C, which is the speed of light, 3 times 10 to the 8, and you're going to divide that by this 5.5 times 10 to the negative 7. And when you do that, you will get 3.6 times 10 to the negative 19. We've got two significant figures there. The reason why we use two significant figures is that the most inaccurate value that we're looking at here, this 5.5 and all of these values are to the lowest one is to two significant figures. So two significant figures is fine. That's in joules. If we wanted to put that into electron volts, we would have to divide this by 1.6 times 10 to the negative 19, and we would get our answer in electron volts, which would be about 2.3 electron volts. We do that by dividing this value over here by 1.6 times 10 to the negative 19. You divide by that. Looking at the last question here, it asks the ratio of the rate of electron emission to the rate at which the photons are incident on the metal. So we see here that we have monochromatic light. Now this means just light all of one wavelength, and that's that wavelength over here, and we have 3 watts. So we can actually work out from this the number of photons. We can work out the energy of one photon. This 3 watt over here, 3.0 watt, just means 3 joules per second. So if we can calculate the energy of one photon and then divide that into this value over here, you will get the total number of photons per second. So let's just do that. We can use our same formula again, that E is equal to hc over lambda, and we'll put that in. So that's going to again be 6.63 times 10 to the negative 34 times 3 times 10 to the 8, divided all by your wavelength, which is 4.6 times 10 to the negative 3. We get that value. When we do that value there, we get and then we get about 4.3 times 10 to the negative 19 times 10 to the negative 19. I'll keep this value in my calculator, and then I'm going to take here, it's 3 watts. I'm going to divide 3 divided by that value, 4.3 times 10 to the negative 19, and you'll get from that 6.9 times 10 to the 18, and then we're going to find the ratio of that. We look at seeing here, we're looking at the ratio. So we got the emitted amount is 4 times 10 to the 10, and we're going to divide that by 6.9 times 10 to the 18, and you'll get a final value from that of 5.8 times 10 to the negative 9, and that would be the ratio between the two. And then finally over the page you have light from a different source is incident on a metal in B. The new source has a power of 6 watts and emits light of a wavelength of 9 times 10 to the negative 7. State the effect of these changes, if any, on your answer to B1. Well, because this is 9 times 10 to the negative 7, and it's greater than the 5.5 times 10 to the negative 7, which was your threshold wavelength. Therefore, no electrons will be emitted. Okay, so it would not give the required energy for the work function.